You ever hear a rumor that the B-2 Spirit is basically invisible? It isn't magic. It's the result of decades of science, design trade-offs, and a relentless focus on one goal. Don't get seen until you've already hit your target. To understand how the B-2 became invisible, we need to walk through a story that blends aerodynamics, materials science, systems integration, operational tactics, and strategic thinking. This is not a manual or a blueprint. It's a high-level look behind the curtain at the engineering decisions and doctrinal choices that turned the B-2 into one of the most enigmatic aircraft of its era. Start with the why. In the Cold War, the ability to penetrate defended airspace was everything. Surface-to-air missiles and radar networks matured rapidly after the 1950s. Traditional heavy bombers had to fly high and fast, or low and fast, or rely on numbers and escorts. But the game changed when air defenses grew sophisticated enough to deny access to entire regions. The theoretical solution was simple: reduce the chance the enemy detects you in the first place. If radar and infrared and visual cues can't reliably see you, you can do missions that otherwise would be suicidal. That strategic need drove investment into stealth, a discipline that asks, how do we make an aircraft less visible to detection systems? The B-2 is the culmination of that effort in the bomber role. The aircraft's shape is the first, most obvious answer. Early stealth thinking showed that straight edges, vertical tails, and exposed engine faces create strong radar reflections. The B-2 abandons conventional layout entirely in favor of a flying wing. No vertical stabilizers, no abrupt fuselage wing joints, no exposed weapon bays when closed, and surfaces blended to avoid angles that scatter radar waves back to their source. This shape drastically reduces the radar cross-section from many detection aspects. But shape alone isn't enough, because any real airplane needs engines, inlets, exhaust, landing gear, and seams, all of which can betray it. That's where materials and coatings come in. The B-2 uses advanced radar-absorbent materials, RAM, and specialized surface treatments to soak up or scatter radar energy instead of reflecting it. Think of it like acoustical insulation for radar. Instead of bouncing the signal back like a mirror, the skin and coatings redirect or dissipate energy so the return is much weaker. These materials had to be developed in tandem with the aircraft's structural skin. The skin needed to be a load-bearing surface, an aerodynamic surface, and an electromagnetic filter all at once. Engineers worked to integrate RAM into composite structures and to develop paints and surface treatments that could withstand the stresses of flight and the environment while maintaining stealth characteristics. But stealth isn't just passive. The B-2's designers paid extraordinary attention to managing the heat and exhaust signature, the infrared problem. Engines are hot, and hot things glow in the infrared. To avoid becoming visible to IR sensors and heat-seeking missiles, the B-2 positions its engines inside the wing's upper surface and mixes exhaust with cooler air so the plume dissipates before it can be easily detected. Exhaust geometry, baffling, and the airframe design all help lower the infrared contrast between aircraft and background, especially against ground clutter or oceanic backgrounds where the thermal contrast can be exploited. Again, the goal is not total invisibility, that's impossible, but lowering the signature below detection thresholds or confusing the sensor enough to make targeting unreliable. The aircraft's external features were also minimized. Weapon carriage is internal. There are no big pylons or exposed stores that would reflect radar. Landing gear doors and access panels are precision designed to close flush and avoid creating sharp radar returns. Even the way the airplane opens its bomb bay is designed with stealth in mind, minimizing radar exposure during weapons employment. Everything is a trade-off between operational necessity and signature management. But the B-2 didn't stop at shape and materials. It's a systems story. Sensors, communications, navigation, and onboard processing were integrated to minimize electromagnetic emissions. Radar warning receivers, communications suites, and navigation systems are designed to operate with the least possible detectable output, using low probability of intercept techniques and passive sensors whenever possible. Sometimes the most telling thing an aircraft can broadcast is its own radio signals, so part of stealth doctrine is emissions control. When you don't speak, you're harder to locate. That's why B-2 operations emphasize strict radio silence, pre-planned routing, and mission profiles that avoid vulnerable windows. Electromagnetic warfare plays a supporting role. The B-2 can operate in concert with EU assets that jam or spoof enemy radars, creating local conditions that reduce detection risk. But the idea is that the platform itself is a low observable baseline. It is a force multiplier, not the primary cloak. Combining low observable design with EU and operational discipline compounds survivability. The fewer things an adversary can queue on, the more options the B-2 crew has. Maintenance and sustainment are a critical, often overlooked piece of the stealth puzzle. The coatings and materials that make the B-2 less visible are not maintenance-free. Stealth requires meticulous attention, keeping skins smooth and joints sealed, repairing micro-damage, and applying controlled materials in climate-controlled hangars. This is why stealth fleets have unique basing requirements, and why sortie generation rates for stealth aircraft can be influenced by how quickly and precisely crews can service the aircraft's low observable properties. The invisible B-2 is also a logistical achievement. Sustaining stealth is as much about paint booths, quality control, and careful handling as it is about initial design. Operationally, the bomber's force multiplier is planning and tactics. The U.S. Air Force developed mission planning that routes B-2s through corridors of least detection probability, exploiting terrain masking, radar line-of-sight limitations, and windows of degraded enemy coverage. Pre-strike intelligence identifies radars, their look angles, and their frequencies, so planners can avoid exposing the aircraft to the most sensitive axes. When the B-2 flew over Serbia in the 1999 Kosovo campaign, or when it long-range integrated air defense systems, it did so as the tip of a carefully choreographed spear. Electronic suppression, decoys, timing, and diversion all play roles in reducing the aircraft's exposure. Let's be clear about what invisible means here. The B-2 is not unseen in the cinematic sense. With the right sensors and tactics, adversaries can and have detected stealth aircraft. What stealth does is alter the economics of detection. It raises the bar. You need better sensors, more sophisticated processing, and greater risk tolerance to track and engage a low observable target reliably. Instead of being the first thing noticed, the B-2 becomes ambiguous on a radar screen, a whisper rather than a shout. And ambiguity is an operational advantage. Ambiguity breeds delay. Delay breeds decision friction, and decision friction gives military planners precious time. The B-2's avionics make that ambiguity exploitable. The aircraft's integrated avionics and navigation allow precise timing and weapons delivery, even when the crew deliberately avoids active emissions like radar. In practice, a B-2 can navigate via inertial and stellar or satellite aids with careful emission control, reach the target area, and release precision munitions with high probability of success. Precision weapons mean you don't need to expose yourself for area bombing. You can take one pass and leave. That surgical approach reduces risk to the aircraft and also reduces collateral damage, depending on the chosen weaponry and tactics. Speaking of weapons, stealth shapes the ordnance environment too. The B-2 can carry a mix of conventional precision bombs and standoff munitions internally. The internal carriage preserves stealth until weapon release. When long-range standoff weapons are employed, the B-2 can launch them without having to overfly the most dangerous zones. That alters the strategic calculus. A stealthy bomber can be a force for preemption, shaping the battle space before less stealthy assets move in. Intelligence matters. From early development through operational use, the B-2 project relied on a deep appreciation of adversary detection systems. Designers studied radar frequencies, pulse repetition rates, antenna geometries, and sensor integration to understand which aspects of RCS reduction mattered most. This is why the B-2 is most effective against legacy radars and still presents challenges for modern arrays. Reducing early queues and complicating returns is a nuanced arms race. As sensors advance, so do countermeasures. We should also talk about cost and strategic choice. The B-2 is expensive, not just to build, but to operate. Every stealth feature has a cost: manufacturing complexity, maintenance overhead, and constrained payload geometry. In practice, that meant a small fleet and a heavy emphasis on strategic missions where survivability mattered most. The US chose quality and capability over quantity. Better to have a handful of planes that can go anywhere and survive than many that are easily shot down. That strategic trade-off speaks to the role of the B-2 as a national asset rather than a tactical commodity. There's a human element too. The aircrews and maintainers had to be trained for a paradigm that values silence, patience, and precision. Flying low observable aircraft requires discipline, the right pre-flight checks, the right taxi paths to preserve skins, the right sealing of panels, and the right decision-making in the cockpit. Psychological conditioning and training were part of the program. Crews had to anticipate that the worst outcome was being detected and targeted, and they practiced how to respond with appropriate evasive and emission control measures. Over time, technologies evolved. The B-2's baseline was set decades ago, but updates in processing power, sensors, and networking have improved mission flexibility. Advances in materials and maintenance have made sustainment more practical, and integration with modern situational awareness tools allows B-2 crews to work within a broad combined arms approach rather than as isolated ghosts. Cyber and networked warfare have also become relevant, protecting the aircraft's information systems from intrusion and ensuring the integrity of mission data is as important as physical signature management. But the most interesting piece of stealth evolution is not merely technology, it's adaptation. Adversaries learned to look for other signatures, gaps in coverage, correlated faint returns across multiple sensors, acoustic cues, and even patterns of logistic movements. That led to a cat-and-mouse game. Stealth designers reduce obvious cues, adversaries invest in sensor fusion, and planners seek ways to complicate detection further. The result is not perfect invisibility, but increasing cost and complexity for anyone trying to detect and track a stealthy bomber. Real-world operations demonstrated the concept. During conflicts where the B-2 deployed, it achieved key psychological and operational effects. The ability to strike high-value targets deep inside defended airspace with minimal forward basing, the demonstration effect of a platform that seems to come out of nowhere, and the tactical flexibility of delivering precision at long ranges. Political leaders and planners valued this capability because it offered options that would otherwise demand far larger force packages. Ethics and optics are part of the story too. The ability to strike unseen raises questions about decision authority, accountability, and international law. Stealth changes the political dynamics of intervention. If a nation can strike with reduced attribution risk, the calculus of use changes. Transparency, rules of engagement, and strategic communication all become important when a strike is difficult to attribute or when the political costs of discovery are large. Looking to the future, invisible is evolving. Sensor networks get denser, passive detection improves, and machine learning sifts more signal from noise. To stay ahead, stealth will likely remain a multi-domain problem combining passive, low-observable design, active countermeasures, cyber resilience, and tactical innovation. Platforms like the B-2 may be reinforced by unmanned systems, decoys, and distributed strike packages that multiply the effectiveness of any single bomber while diluting the risk. So, what's the takeaway? The B-2 didn't become invisible because of a single trick. It's the product of a systems approach. Shape, materials, heat management, emissions control, operational discipline, integrated avionics, and careful sustainment. You remove any one of those pieces, and the invisibility degrades. Put them together, and you create not absolute stealth, but operational advantage, the kind that reshapes options on a battlefield and gives commanders the ability to act where others cannot. Finally, the B-2's legacy isn't just technical, it's conceptual. It demonstrated that survivability could be engineered into an aircraft through design choices that alter how sensors perceive it. It reshaped procurement thinking, emphasized multidisciplinary collaboration, and forced militaries worldwide to rethink both offense and defense. Stealth forced sensors to improve, which forced stealth to evolve, and that iterative tension continues to define air power in the 21st century. At the end of the day, invisible is shorthand for a carefully cultivated asymmetry. Fewer cues, more doubt, more time. That's the strategic fruit of the B-2 program. Its true power lies not in a cloak of science fiction, but in the accumulated advantage of hundreds of design choices, rigorous discipline, and an operational doctrine that turns reduced detection into decisive capability. When you put all those pieces together, you understand why so many leaders and engineers poured decades of effort into making a bomber as hard to find as humanly possible, because sometimes the best way to win a fight is to be where the enemy least expects you to be. Thanks for watching. If you found this breakdown useful, don't forget to hit that like button, share it with a friend, and subscribe for more deep dives made simple. Drop your thoughts in.